Now we're in section 3.3 and we talk about vertical stretches and compressions. This is where we take a function and we're going to stretch it vertically or maybe compress it vertically, and that will be the transformation that we do. And it reminds me of when I was a kid, there was a toy called Stretch Armstrong, and you could stretch him and it looked totally weird, and you could stretch it all sorts of ways. But that's the idea of what we're going to be doing here with these functions is we're taking them and they're going to look different. For the first time, they're really going to look different than they looked before. Up until now, we've been doing kind of rigid transformations where the basic shape of the function, with these shifts and even with the reflections, the shape stays rigidly what it is. But for the first time, we're going to stretch it and compress it in a way that the function itself really starts to look different than it did before. The first example we're going to look at is the parent function is going to be f of x equals x squared. And we're going to think of, what if we took that function and multiplied it by 10? How does that affect things? And this parent function looks something like this. It's this parabola where it bottoms out at 0, 0. So essentially the function g of x is, we're taking f of x and we're multiplying every output by 10. So every y value gets multiplied by a factor of 10. Think about what you think that might look like. If for any x value, the y value is getting multiplied by 10, if that y value was a 1 before, it's now a 10. If that y value was a 2 in this function, it's now a 20. So the y values are really skyrocketing up. And so the function starts looking like this. It's a really skinny version of itself. And it still opens up like a parabola, but it shoots up so quickly, shoots up so high so quickly that it is really stretching this guy up by a factor of 10. Okay, let's take a look at this function now, this f of x, and here's the formula for the function. It's kind of a big old long function. In the last example, we saw that if we multiplied a function by 10, it really stretched it up high. All the y values became really amplified. Let's see what multiplying this function, let's just multiply it like by 5 and see what happens. So I haven't graphed it yet, but I've created a new function, y equals 5 times f of x. And think about what that would mean for all these positive y values. Where would they go? Here's a y value of about 1 right here. Where is it going to go when we multiply this point by 5? And what's going to happen to these x values down here? Where will they go? Will they go up? Will they go down? So let's graph it and we'll see if what you thought should happen did happen. This is the function, the green one is the function 5 times f of x. And it is a vertical stretch of f. So for example, right here, this point 1, 1. This is actually the point 1, 1. Okay, so here we've got our functions. Let's zoom in on what's going on. So right about here is the point 1, 1. And green is the stretched out version. And it got stretched for that x value, it got stretched to 1, let's see, 5. And that sounds right. The y value should get multiplied by 5. That's what this right here is saying, that every y value is going to get multiplied by 5. Let's just check out another one. This guy right here, well, let's not pick that one. That's already, this looks like a y value. Let's see, that would be 0.4 and about, I'm guessing it's like probably 0.8-ish. Okay, and so when that point gets stretched by a factor of 5, the x value stays the same, it's still 0.4, but the y value should technically get multiplied by 5. And let's see, 0.8 times 5 would be 4. So this y value gets stretched all the way up to here, which now has a y value of 4, and that looks about right. This new point that it got stretched up to is 0.44. Okay, so all of these points are getting stretched up. At least the positive ones are getting stretched up by a factor of 5. And so the larger the number, you know, the more the stretch that's going to happen. So like, for example, you know, this has a y value of 4. It's going to get stretched all the way to a y value of 20. So no longer do we have these rigid shifts. The shape of the graph really is changing. The green graph does not look like a, you know, a carbon copy of the red graph. Things are getting stretched differently depending on what your y value was, and how it got stretched. You can even see it here. Like here we got stretched a little bit more than 3 units, but here we got stretched 4 units up. Okay, and then the negative numbers are doing something completely different. So here is a, let's see if we could take, yeah, let's take this one right here. Let's estimate what that would be. Let's see, that's going to be about 1.4, I don't know, 2 is the x value, and then the y value will be 0.5. And when I stretch it, it's going to stretch more negative. And I would expect the x value stays the same, but this should go to about the 0.2.5, because it needs to stretch by a factor of 5. So this y value would get multiplied by 5. And when that happens, when it gets stretched to the new green graph, you know, does it get stretched? It goes about right here. So that's its new point, is right here. So the new point becomes, you know, gets stretched to the point 1.42. No, this is a negative 0.5 up here. Yeah, that says negative 0.5 and negative, let's see, this is negative 2.5. Okay, so that worked exactly as it should have also. So each of these is getting stretched a different amount. This got stretched 3.2 units. This got stretched 4 units. This only got stretched negative 2 units. And that's because it really depends on, the y value that you're starting with. Whatever y value you're starting with will determine how much of a stretch you get, because this y value gets multiplied by the 5, and that'll be different for each y value. So these stretches, the shapes of the graphs are changing. Now we're going to multiply f of x by 0.2. This is a number that's smaller than 1. It's 1/5. What would you think will happen to, remember the red graph is the original function. In fact, let's take off the green graph for right now. So when we do this, we're multiplying, this is some sort of vertical thing happening. All the y values are getting multiplied by 0.2. It sounds like this is going to be more of a compression, where things get smushed down close to the x-axis, because every y value is getting to be just 1/5 of its value. And so think about what the picture of this red graph will become once we do this. It is going to end up being a compression. So is this what you thought it should look like? Remember, the red graph is the original parent function f, and then this purple graph is the new function that's really a compression of that red graph. We multiplied it by 0.2, so that means that every y value should have gotten smushed down to 1/5 of what it was before. Let's do a little let's test out that idea. Let's see, this right here is, we decided that's a 0.11, and so in that compression it got pushed down to this point, which looks about like 1, and that is probably about 0.2. And that's right, that's the y value should get compressed to 0.2 of what it was before. Let's take a little bit higher. Let's take this point here. So this point would be, let's see, 1, 2, 3. That is negative 0.6 for an x value, and 4.5 for a y value. So when I do the compression, it gets moved to this point right here, which is just slightly below that hash mark. And this will be the point negative 0.6, and it'll be about 0.9, which is 1/5 of the original y value. So that y value got compressed to 0.9. Same story over here. You know, these negative y values are going to act in a similar way. So for example, let's take, how about this guy right here? This will be the point 1.8. It'll be slightly less than 1.8, and the y value is -4. So think for a minute what you expect this y value to get compressed to. It's getting multiplied by 0.2, which is the same as getting multiplied by 1/5. So -4 times 1/5, that's a -4/5. So it should get compressed to a point that is just slightly below -1. And so we'll see if it does. It gets compressed, compressed, compressed. Okay, and that y value is, this is 1 right here, so yep, that looks about right. This would be the point 1.8, negative about 0.8. And this number is 1/5 of this number. So again, these points, as they're going through the transformation, each of them travels a different, you know, the difference in their y values is a different amount depending on where they started, because these stretches and compressions are factors instead of just these rigid motions. And so the graph itself changes shape. We're going to generalize what we found, and you in your own minds probably already know how to generalize these ideas. You know, we knew what happened when we multiplied it by 5, and we knew what happened when we multiplied it by 0.2. Here's where we multiplied it by 5. This green line is what happened. And when we multiplied it by 0.2, here's this purple line. That's what happened. So we want to be able to generalize these vertical stretches and compressions. So the graph of, we'll call it a new function g of x, but the important thing is some number is getting multiplied by our function f, our main function f. So a times f of x is the graph of f of x stretched or compressed vertically. So the stretching and compressing, which one it is, will depend on what this number here looks like, by a factor of, and we'll say absolute value of a units because it's possible that this is a negative number. Whenever you see the word factor, think multiplication. It's not as if we're adding this number, you know, we're not shifting it up and down a units. It's being multiplied by the function, so every y value, it's being multiplied by each output of this function. So each y value is getting multiplied by the absolute value of this number. And so we'll say if some condition is met, then it's a stretch. And we want to think, what is it that makes it a stretch instead of a compression? It was all dependent on this number. Remember, when it was a 5 here, it was a stretch, and when it was a 0.2, it compressed the function down. And so the condition is actually if a is greater than 1, then it's a stretch. And we go a little further, and we want to say if the absolute value of a is greater than 1, it's going to be a stretch. And the other side of things, how do we make it so that it's a vertical compression? This one was a compression. Everything got smushed down closer to that horizontal axis. A vertical compression will take everything and smush it down by a factor towards that horizontal axis. And the condition that makes it a compression instead of a stretch is if a is smaller than 1. The absolute value of a is smaller than 1. So we now add these to our catalog of transformations of functions. We've seen, you know, rigid shifts up, down, left, right. We've seen these reflections across vertical axes and horizontal axes. And now we see vertical stretches and compressions. Okay, for our next example, we're going to think about the point 1, 3 being a point on the graph of a function f of x. And we're going to look at a series of transformations, and we're going to find out where this point 1, 3 travels to under each of the transformations. And here's our first transformation. Okay, I'm remembering from last section that this is some sort of reflection, And let's see, we're switching x values for negative x values. So this is a horizontal reflection, a reflection about the y-axis. So if 1, 1, 3 is a point on the graph, it's going to get reflected across the y-axis. It's a horizontal reflection, and it should travel to the point negative 1, 3. So we've answered their question. The 0.13 under this transformation gets moved to negative 1, 3. Okay, how about under this transformation? This is a transformation that the only thing going on here is this negative 7. That's a vertical shift down 7 units. So 1, 3 where it is originally, it's going to go down 7 units, just straight down. And where will it land? Let's see. 3 minus 7, that's going to land it at negative 4 for the y value. Does the x value change? It shouldn't. It's just going vertically straight down. So under this transformation, 1, 3 gets transformed to the point 1, negative 4. Okay, so here's an interesting one because it looks like we've got a couple different transformations going on here. We've got that it's getting stretched vertically by a factor of 5. And we also have this transformation, which is a horizontal shift, and it should be a shift to the left 3 units. We'll take this one first because it is a transformation having to do with the input, and then we'll do the transformation on the output second. So first of all, this horizontal shift to the left 3 units, we are at the point, we start at the point 1, 3, and we're going to go left 3 units, 1, 2, 3. And so that should get us to the point negative 2, 3. But we're not done yet. We still need to do this vertical stretch here on the output of this. So negative 2, 3, and we're doing a vertical stretch. So the y value, if you're doing a vertical stretch, if you're at negative 2, 1, 2, 3 right here, and you're doing a vertical stretch, then it's only that y value that gets affected. And should we add 5? Should we multiply by 5? We definitely want to multiply by 5 because these vertical stretches are by a factor of that number. So 3 is going to get multiplied by 5, and the new y value will be 15. So our x value stays the same, negative 2, but our y value gets stretched to the y value 15. Okay, we'll do just one more, and it looks like we have possibly 3 things going on here. We've got some sort of reflection, then some sort of vertical stretch or compression, and then this negative is going to be another type of reflection. So again, we'll start with the input and see what's going on with that. We begin at 1, 1, 2, 3, and this negative x that's in here will, the negative is going to be a horizontal reflection. So that's a reflection across the y-axis, a horizontal reflection. And whereas we were at 1, 3, now we're at negative 1, 3. So that's the first thing that happens. Okay, then we have to deal with the... Okay, so we've dealt with that negative. We're going to deal with these guys now, and we'll start with the 1/4. We actually could do either of these first, but we'll take care of this vertical stretch or compression. It looks like it's going to be a compression because its absolute value is less than 1. So if we're at the point, now we're at the point negative 1, 1, 2, 3, right there, and we're going to compress this point vertically by a factor of 4. That means we're dividing the y value by 4. So 3 is its y value, and it gets compressed by a factor of 4, which takes it down to 3 divided by 4, or 3/4, or 0.75. So that is the compression that happens. Its x value stays the same. It's still at negative 1. It's just the y value that gets compressed down to 3/4. Okay, so we start at 1, 3. We got reflected over to negative 1, 3. We got compressed down to negative 1, 3/4. Last but not least, we got to take care of this little guy. This negative, it's sitting outside of the function, and so it is a vertical reflection. It's a reflection across the horizontal axis. So this is going to take this point that we're at right now and reflect it across the the horizontal axis. So here we are at negative 1, 3/4, and we need to do a vertical reflection, so it takes it right across here. Let's see, where would we land? We're still at negative 1, but now we land at negative 3/4. So this was the journey of this little point. It went through all these transformations and finally landed at -1, -3/4. It went through a horizontal reflection, a compression by a factor of 4, or a multiplication of 1/4. Either way you look at it, is fine. And then it went through this vertical reflection and landed right here finally. Before we leave this section, I want to get through just a little bit more practice using these tables and evaluating these function expressions. So in this example, we're asked to use the table to evaluate this guy. And he shows up in this section because it happens to be a vertical compression of this function. We really don't need to know that in this example because we're strictly going to use the table and use what we know about function notation. But that is why it shows up in this section, is because this is literally a vertical compression. Okay, so we're going to evaluate this when x equals 3. And so to do that, we're just going to start plugging in things that we know. We know that x equals 3, and so we're going to start by, this is not an equality. It's not like an equation we're trying to solve. We're just trying to simplify this expression, and hopefully it'll spit out a number in the end. So the thing we're going to start with is knowing that x equals 3, we'll just plug it right in here for x. If this is x, then it should be able to be replaced by 3. And when we do that, we get 1/3 f of 3 minus 6. And that just becomes 1/3 f of -3. Okay, at this point, f of -3 is something that we could use the table to evaluate. When -3 is our input, what is the output of the function f? When -3 is our input, oh, here it is right here. When -3 is our input, what's the output of f? And it's 10. So this guy right here is 10. And we still have the 1/3 being multiplied by it. So this equals 10/3. And that is the solution to the problem. For our next example, part B, we're asked to solve the equation for x using the table of this guy. And now this is a big long equation. There's a lot going on. There's this function sitting in here and a bunch of numbers all over the place. So this time they don't give us an x to plug into here, but they say go ahead and please find what x is, knowing this relationship. So the thing that we're going to do is clean all of this up as much as we can. We're going to isolate this, hopefully. And so cleaning it up means kind of stripping away the numbers that are attached to this. And we can strip this guy away and strip this guy away and just move it to the other side. So first, just adding 5 to both sides. F of x plus 2, -5 plus 5 will go away, and then we have -4 plus 5. And so this becomes 1/4 f of x plus 2 equals 1. Okay, let's see. We really want that f of x plus 2 by itself, so we'll multiply both sides by 4. And on the left side, this becomes a 1, and we just have f of x plus 2 equals 1 times 4, which is 4. Okay, this is the point at which we're going to use the table, and we really have to, this is probably the big cognitive jump of the problem right here. Something has an input, well, some input has an output of 4. Okay, in this table, do we ever get an output of 4? As we look at all the possible outputs, yeah, right here, we see that actually f of 2 is 4. So 2 gives us an output of 4. But here we also know that f of this guy, this thing, equals 4. So it must be the case, this is kind of the big logical jump in this problem, it must be the case that this inside these parentheses has to be equal to 2. So we can say then x plus 2, that input has to be equal to 2 because each of them are giving an output of 4. It's the only time it happens in the table, and so this relationship must be true. This input has to equal this input. They're both giving the same output, and it's the only time that it happens in the table. Okay, from here, this is super nice because now we are able to do the thing that they're asking us to do, which is to solve for x, and I'm just going to subtract 2 from both sides, and I get that x equals, let's see, 2 minus 2 is 0, and that's it. That's the solution to this problem. Before we end this section, I want us to think about this question here. What will a vertical stretch or compression do to a point that's on the horizontal axis? So say that you have some function, not that one, how about this one? Okay, you've got some function f of x, and maybe we want to think about what is 5 f of x. And specifically, I want to know what is it doing to this point right here? Say that that's the point 1, 0. In this vertical stretch of a factor 5, where does this guy go? So that's a question I'm going to leave for the quiz, but think about this vertical stretch really only affects the y value of the function. And so this is an important note to make. The points that are sitting on that horizontal axis, something slightly different but expected happens to them during a vertical stretch or compression. So the big ideas that we saw today were, first of all, the idea of vertical stretches and compressions is by far was the biggest idea. We know now how to recognize them and how they really can change the look of a graph. And we got some good practice predicting where a point would travel through sometimes multiple transformations. And we also got more practice with using tables and interpreting what the function notation means.